After discussing how a Karnaugh map is constructed, let's now study the method for using this table for the two-level synthesis of a combinational function. The Karnaugh's method consists of two distinct phases. The first phase aims to identify all the prime implicants of the function. We will define shortly when an implicant is considered prime. The second phase, which involves identifying the minimal subset of prime implicants necessary to cover all the ones of the function and thereby define the solution. Let's start with the first phase. Based on what we have studied in the previous modules, we can identify an implicant on the Karnaugh map as a grouping of 2 to the power of n adjacent minterms. Let's take an example. Let's consider the following function, for which we show the Karnaugh map. Here is an example of a grouping of two ones. Here is another one, which reminds us that the first row of the map is adjacent to the last one, as they are at a Hamming distance of 1. Additionally, let's remember that the involvement of the same minterm in multiple groupings, as occurs here, is possible thanks to the application of the idempotence property. Here is a grouping of 4 minterms in the same row. Of course, there can also be groupings of 4 minterms in the form of a 2 times 2 grid. Finally, the one shown in red is not an implicant, as it groups a number of minterms equal to 3, which is not a power of 2. Let's remember that the reduction rule applies to pairs of product terms, so its iterative application involves 2 to the power of n minterms. Once an implicant is defined as a grouping on the map, we define a prime implicant as a grouping of maximum size, meaning it cannot be further expanded into a grouping of a larger size by using the simplification rule previously studied. Thus, a prime implicant is called essential if it covers at least one minterm that is not covered by any other prime implicant. In conclusion, we have defined 3 different types of groupings: implicants, prime implicants, and essential prime implicants. Note that the relationship between the 3 sets is that the set of prime implicants is a subset of the set of all implicants. In fact, this last one also includes all minterms and all the other groupings we can generate by iteratively expanding from the minterms. Then the set of essential prime implicants is a subset of all the prime implicants. Here is an example. We show all the prime implicants in orange. You can see how it is not possible to further expand these groupings. Among all these prime implicants, we notice 2, now in green, each of which is unique in covering a 1 of the function. Once an implicant is identified, we need to write the corresponding product term expression. The procedure is as follows. Consider an implicant that covers 2 to the power of n minterms for a function with m variables. Identify the m minus n variables that do not change value between the minterms in the grouping. For each of these variables, if the constant value it takes is 1, the variable is added to the expression of the product term in its positive form. If it is 0, it is added in its negated form. Let's revisit the example map used earlier, where we highlight a single implicant for the sake of clarity. The function has 4 variables, and the grouping consists of 2 to the power of 2 minterms. Thus, the corresponding product term will have 4 minus 2, which equals 2 literals. On the row indices, we note that A changes value between the first and second rows of the grouping, while B remains constant at 1. On the column indices, we note that C remains constant at 1, while D varies in value. Therefore, we take B and C in their positive form, and we obtain the product term BC. In summary, the expansion phase consists of the visual identification of all the prime and essential prime implicants. As we discussed, we first identify all the implicants by finding the groupings of maximum size. Then, we classify as essential primes those implicants that are the only ones covering at least A1 on the map. For each implicant identified, the corresponding product term is then calculated. Let's revisit the example. We have drawn the map for the function. We identify the groupings of maximum size. Additionally, we identify the subgroup of groupings that are unique in covering at least an element of the onset. These latter ones are the essential prime implicants, for which we show the product term expressions on the right. The remaining ones are the prime implicants, and we also provide their product term expressions. Let's proceed with the second phase. The goal of the second phase is to identify an expression in the form of sum of products composed of the smallest subset of prime implicants such that all the minterms are covered. We remind you that we are looking for a solution in terms of a sum of products because this is the chosen reference model in accordance with the starting expression that is represented with the first canonical form. Therefore, the optimized cost criterion is the cardinality, that is, the number of implicants, which essentially corresponds to the number of gates with a generic number of inputs required to implement the circuit. Furthermore, if there are multiple solutions with the same number of implicants, the selection proceeds by minimizing the number of literals. Why do we construct the solution using only the prime implicants? There is a theorem, which we do not prove here for brevity, that states that for a given two-level combinational synthesis problem, there will always be an expression in the sum of only prime implicants that is minimal with respect to the cardinality. The definition of the solution starts by selecting all the essential prime implicants. Since each of them is unique in covering at least A1 on the map, their selection is mandatory. Next, all the prime implicants that cover ones, which are all already covered by the implicants just selected, are eliminated. These eliminated implicants, known as completely redundant, are not necessary for the coverage, and selecting them would only result in a higher cost. Let's revisit the previous example. We select the implicants A and B because they are essential. Specifically, A is the only one covering the position 0, 0, 0, 1, which represents minterm 1, while B covers the position 1, 1, 1, 1, which represents minterm 15. Consequently, we can notice that D, the implicant covering the second row, is completely redundant, as its ones are already covered by A or B, and therefore it can be discarded. The next step is to select the smallest number of remaining prime implicants to cover all the ones that have not yet been covered. If there are multiple possible solutions with the same minimum cost, the solution that minimizes the number of literals is selected. It is important to note that the choices should be made based purely on an observation of the map. Once the solution is identified, all the remaining implicants are discarded for the same reason as before. These implicants are called partially redundant. Finally, we would like to point out that if the solution consists only of essential prime implicants, this second pass on the map is not performed, and the solution is unique. Let's continue with the previous example. We have removed from the map the ones covered by the implicants already chosen. So the map now only contains the ones that still need to be covered. Among the three remaining prime implicants, F can be chosen as it covers the two remaining ones, and therefore C and E, which are partially redundant, are discarded. To conclude the example, we show the expression of the solution, which is the sum of the product terms corresponding to the selected prime implicants and the obtained cost. As we studied in previous lessons, the don't care set represents a set of conditions of indifference that can be used as degrees of freedom in the optimization process, potentially leading to a solution with even lower cost compared to the one obtained by considering only the onset. The Karnaugh's method handles don't cares as follows. In the first phase, we treat the don't cares as ones so that we can use them to maximize the size of the prime implicants and potentially reduce their number by merging more implicants that were previously separate. In the second phase, we focus only on the ones for the selection of prime implicants. A don't care is covered only if an implicant covering it is necessary to cover a one. It should also be noted that since we want to cover only the ones with the fewest implicants, if a grouping covers only don't cares, it is not considered an implicant and is discarded at the end of the first phase. Here's an example. We find two implicants in green, each of which has been expanded to include the don't cares, while in red the grouping represented by the product term not A, not C, is not an implicant because it only covers don't cares. Thus, we obtain the solution shown here. Sometimes the criteria of essentiality and redundancy that we studied do not allow us to identify a solution on the map. Such a map is called cyclic. In this case, we proceed arbitrarily. Let's clarify the case with an example. We show all the prime implicants. We can notice that no choice can be made. So we arbitrarily choose the first prime implicant in the top left, shown in orange. Then, in cascade, we choose all the other implicants shown in orange, while the ones in green have become redundant. We list the resulting expression on the right. However, we could also have chosen the green implicant on the first row, and in cascade, we would have selected all the other implicants in green, leading to the solution now shown. In conclusion, there are two different solutions with the same cost, both equivalent, from which we randomly choose one. Finally, let's analyze the case of a function with 5 variables. The Karnaugh map has 3 dimensions, with 2 tables stacked on top of each other. Each table represents 4 variables, and the 5th variable identifies one table with 0 and the other with 1. So, the groupings can be done in 3 dimensions. Here's an example. We use the variable a to distinguish between the 2 tables. Notice that with a equals to 0, we identify the table on the left, and with a equals to 1, we identify the table on the right. Then, we can identify implicants by expanding the grouping on a single table, as done here for the orange grouping on the left or the green one on the right. In constructing the product term, the variable a will appear negated if the grouping is on the left table, and in its positive form if it is on the right table. Additionally, we can identify a grouping that expands in the 3rd dimension when the same elements are grouped on both tables, as seen at the top right on both tables. In this case, having expanded in the 3rd dimension, the variable a disappears from the product term. And here is the expression of the solution. We can apply the same approach in the case of 6 variables. But in that case, we would need to use 4 tables. As you can see, the process becomes even more laborious and practically impossible to apply with a higher number of variables.